Hello, I am happy to see you once again on the Thinking Mathematics channel. Let's have some thinking on number-based conversions. Let A be a perfect power of some integer b. What I mean by that is, there exists some integer c such that a equals b exponent c. Then, when we write a in base b, we'll have c plus 1 digits. How does this work? That is, it will be 1 followed by c of the zeros. So 1 up to c times. We can index it 1 up to c. For example, we know that 8 is equal to 2 exponent 3. And so in base 2, 8 will be 1 followed by 3 zeros in base 2. Similarly, since 81 is equal to 3 exponent 4, we have that 81 in base 3 will be 1 followed by 4 zeros in base 3. Another example, 25, that is 5 squared. And so 25 in base 5 is 1, 0, 0. 16 is 2 exponent 4. And so 16 in base 2, 1 followed by 4 zeros. That is 16 in base 2. Now, 16 is the smallest number that when expressed in base 2 will give us the 5 digits. 8 is the smallest number that gives us the 4 digits. So 8 starts the 4-digit group, 16 starts the 5-digit group, 32 will start the 6-digit group, and so forth. It means that from 8 up to 15, all the numbers there, when expressed in base 2, are going to have 4 digits. And so if we know our powers and we are asked to find the number of digits if a given number is expressed in a given base, we are good to go. For example, if you are asked to find the number of digits if 70 is expressed in base 2, that is not a problem. We know that 2 exponent 6 is less than 70, and 70 is less than 2 exponent 7. So for this number, we are going to have 7 digits, that's 64 in base 2, 1 followed by 6 zeros. So the same will apply to 70, the same will apply to 71, up till we get to 127. So it is not a problem. What if we are asked to find the number of digits if 240 is expressed in base 3? Here we know that 240 is less than 243, and 243 is equal to 3 exponent 5. And 240 is also greater than 3 exponent 4. So for 3 exponent 4, we are going to have 5 digits. So the same thing will apply to 240. So we have 5 digits, not a 5 here, but somehow they coincide. Now, assume we were asked to find the number of digits if 250 is expressed in base 3. That one will be 6 digits because 243 is 6 digits, and that is what will run through until we get to 3 exponent 6. Having achieved this, the next question I ask myself is, what if I want to write numbers one more than a perfect power in a given base? For example, we know that 8 is 1000 base 2. What of 9? 9 is just 1 more than 8. And so we have 9 to be 100. Instead of the other 0, we have 1 in base 2. 28 is 27 plus 1, and that is 1 more than 3 exponent 3. If it was 3 exponent 3 in base 3, it would have been 1 followed by 3 zeros. So 28 is 1, 0, 0, then 1 in base 3. We can write 65 in base 2. 65 is 1 more than 64. 64 is 1 followed by 6 zeros. And so 65 will be 1, then you have 5 zeros, 1, 2, 3, 4, 5, and then 1 in base 2. So it works very well if we know our powers. Next, having succeeded in being able to write for numbers just 1 more than a perfect power, the mathematician who is constantly looking for patterns, trying to see if he can extend his findings, will now also think of how to write for numbers just before the perfect powers. For example, 7. Now, 7 in base 2. We observe that 8 was 1 followed by 3 zeros. And 8 is what started the 4 digits. And so 7 is what ends the 3 digits. So 7 in base 2 will be 3 digits. And if it is ending the 3 digits, it means it is exhausting all the highest digits in that base. And the highest digit in base 2 is 1. So 7 is just a string of ones, 3 of them in base 2. A related example will be 26 in base 3. 26 is 1 less than 27, which is 3 exponent 3. 27 has 4 digits, and so 26 will have 3 digits. If it is ending the 3 digits, it means it is exhausting all the highest digits allowable, or that are allowed in that base. So 26 is easy to write in base 3 as 2, 2, 2, base 3. We can do something similar for 80. See, 80 comes just before 81. 81 begins the 4 digits for base 3. So 80 ends it. It will end it using the highest digits over there. In base 3, the highest digit is 2. So 80 is equal to 2, 2, 2, 2. 4 of them in base 3. In a similar vein, we can write 124 in base 5. Okay. Another thing I want us to think about is converting a binary number, base 2 number, to an octal number, a base 8 number, directly. It is easy to do this if we have the base 2, base 8 numbers or versions of the numbers offhand. And that is not difficult to have at all. We already know, for instance, that 1, the base 8 is 0, 0, 1, base 2 is just 1, but it helps to write it in 3 digits. And 2 is 0, 1, 0. We have 3, which is 0, 1, 1. We have 4, which is 1, 0, 0. They are all in base 2. We have 5, 1, 0, 1. We have 6, 1, 1, 0. We have 7, which we just saw, and then 8 we saw earlier. 1 followed by 3 zeros, all in base 2. So with this, if we have a string in base 2 to convert to base 8, we can do that easily. Let's look at that. So for example, we want to write 1, 1, 1, 0, 1, 0, 0, 1, 1, a base 2 number, as a base 8 number. Now this is what we do. Because 8 is 2 exponent 3, we group this number into 3 digits, 3 digits, from right to left, and then we do the conversions. So my first 3 from the right is 0, 1, 1, and that is 3 in base 8. Then I go to 0, 1, 0, that is 2. Then the last I have 1, 1, 1, and that is 7. So once you are familiar with them, you don't have a problem. So we have this number in base 2 is 723 in base 8, just like that. Let's look at another example. We have 1, 0, 1, 0, 1, 1, 1, 0 in base 2. And we want to write that in base 8. Again, my first 3 from the right is 1, 1, 0. That is 6. So 6 in base, I'm not done yet. So I move on again, then I see 1, 0, 1. That's 5. I write that. Then you realize you have only 2 left here. That should not bother us. If we like, we can pad it on the left with a 0, 0, 1, 0. That is 2. So we have 2. And so the number 1, 0, 1, 0, 1, 1, 1, 0 in base 2, its octal representation is 2, 5, 6. Another example. Let's have 1, 1, 0, 1, 1, 0, 0, base 2. Okay, And again, we want to write this number in base 8. So we have our first 3, 1, 0, 0, that's 4. So the more we practice, the more familiar we become with these things. Then we move 1, 0, 1, that is 5. Then we are left with 1, so we can just see this as 0, 0, 1, and that is the same as 1 again in base 8. So this number is 154 base 8. You can just imagine that we can convert from base 2 to base 4, and that will even be easier. We can as well convert from base 3 to base 9. Now, if you like what we have done here, and we have done a lot of these things in thinking mathematics, get a copy for yourself, like this video, comment on it, subscribe to it, so that anytime we release a thinking like this, you will be notified, and hit the notification button. Thank you once again for being with us.